Okay, today we are going to discuss the new topic stress develop in thick wall cylinders. Okay, the thick wall cylinders. How we categorize this thick wall cylinders? The the thickness of the cylinder is very much greater than the internal diameter. We can call it as a thick wall cylinders. The example: highly pressurized fluid conveying tubes, okay, hydraulic rams, and gun barrels, rocket launching barrels. These are example for the thick wall cylinders. Okay. In our previous classes, we discussed stress develop in pressure vessels. Okay. The membrane stress analysis method we used to determine the stress develop in thin wall cylinders, sigma T and sigma L and sigma C. But in here is a little bit different. The stress developed in these thick wall cylinders is a function of R. Function of R means the position to position. If you take the cross section of a thick wall cylinder, with the radial direction, stress is vary. Okay, the two different stresses we can identify, radial stress and the tangential stress. The both these are varying with the radial direction. That means the sigma T tangential stress, sigma R radial stress. The both are function of R. Okay. In today's lecture, we are going to obtain equations for sigma T and sigma R. Okay. Consider the general situation. That means the cylinder under external pressure and the internal pressure both. We are going to derive two equations for sigma T and sigma R. Okay. Then these equation we can reduce for cylinder under internal pressure only situation and cylinder under external pressure only situation we can reduce. Okay. First of all, we are going to obtain these two basic equations. Okay. Okay, let's continue today's lecture. Okay, in this lecture we are going to discuss about the stress develop in thick wall cylinders. Stress develop in thick wall cylinders. So, what is meant by the thick wall cylinders? Okay, in previous classes we discussed about the thin wall cylinders. No, thin wall cylinders. That mean this kind of pressure vessels, pressurized fluid containers. Okay, thin wall cylinders. So what do you mean by the thin wall cylinders? First of all, let's actually we discuss this topic in a previous class. So then the thin wall cylinders mean this wall is thin compared to the internal diameter. Okay. So normally we are categorized the thin wall cylinders. The thickness to diameter ratio is less than or equal to 20. We are categorized under thin wall cylinders. Okay. Then stress, the membrane stress analysis method used to calculate the stress developed in this kind of thin wall cylinders. That means if you consider the infinitely small stress element in a thin wall cylinders, the stress developed we can mark in this kind of manner, longitudinal stress, and the sigma c is the circumferential stress. Okay. Using the membrane stress analysis method, we can calculate these, we can obtain the equation if the internal pressure is P, sigma C is equal PD divided by 2T. Sigma L is equal PD divided by T. Okay. Then these are called the thin wall cylinders. The gas containers, uh, fluid containers, fluid conveying tubes, gas conveying tubes, we can categorize under these thin wall cylinders. Okay, the example for the thin wall cylinders. But in this lecture, we are going to discuss about the thick wall cylinders. The thick wall cylinders, what is meant by the thick wall cylinder? This wall is thick compared to the internal diameter. Okay. I will draw the cross section of this this kind of thin wall cylinder. You can see in this time this thickness is very much greater than the internal diameter. Okay, this thickness is very much greater than the internal diameter. Normally we can consider thickness to d ratio is greater than 20. We can analyze this kind of using the thick cold cylinder stress analysis method. That means, for example, this kind of thick cold cylinders, gun barrels, for example, for this kind of gun barrels, then highly pressurized, high pressure hydraulic rams, high pressure hydraulic rams, then high pressure hydraulic conveying tubes, and rocket launching barrels. These are examples for the thick wall cylinders. Okay, then in here the stress develop is not if you take the variable, the radius from the r, the stress develop is not uniform. Okay, that means if you take the certain cross sectional in the radial direction, cross section plane on a radial direction, these points, each and every point the stress is not uniform. The stress develop in a certain point is a function of r. It's a function of r. That means it is vary with the r. Okay, in each and every radial point the stress is varying. Okay, in here we can identify the two different stress develop. Two different stresses develop on this cross-sectional plane. In this direction the sigma t, in a radial direction the sigma r. Okay, both the sigma t and the sigma r are function of r, function of r. Okay, function of r. That means the point to point, this sigma t and sigma r is vary with the radial position. Okay, then first of all we are going to obtain the equation for sigma t and sigma r equations we are going to obtain. Okay, then these high pressure thick cold cylinders are used in different applications, and also it also use situation, some situation it is used as the internal pressure only situation. That means only internal pressure. Then some situation it used as the external pressure only situation. The external pressure only situation. Okay, external pressure only situation. In some situation it used as the both internal and external pressure. Okay, there's the internal and the external pressure also. Okay, the various applications including the string fittings. We are also discussing the string fitting related to these thick wall cylinders. Okay, first of all we are going to obtain the equation for sigma t and sigma r considering the general situation, the cylinder under internal and external pressure both. Okay, then let's move to the, I will draw the illustrative diagram representing these stresses. So unlike, I will enlarge the previous diagram. Enlarge and draw. So let's take, this is our thick core cylinder outer, and this is our thick core cylinder inner. Okay. So then let's take the stress element, the finite dimension stress element we are going to consider. Finite dimension stress element we are going to consider. the stress element. Okay, let's mark the angles. This angle, let's take it as d theta. Then radial distance to this is this surface r. Then the thickness of this stress element, considering the stress element as the dr. Okay. Then let's take this internal radius as the a. Internal radius as a. External radius as the b. Okay. Let's take this point as o. Okay. Then I'm going to mark the stress developed in this stress element. What are the two stresses developed on this stress element? Sigma Tn. Okay. Then in a radial direction, the stress developed sigma r on this phase after dr distance. Sigma r plus d sigma r. Okay, because this is a finite dimension stress element, so we are marking in that way. Okay, let me draw the perpendicular to this radial line. So then in a tangential stresses we can mark in this kind of manner. Sigma t, that means stress acting on this face. I will mark that way. In here also it's a symmetric sigma t. Okay, then this angle is equal d theta divided by 2. Because this is the d theta, then this angle is equal to d theta divided by 2. Okay, so then I will draw this stress element in separately in here. So I will draw the three-dimensional view of this stress element. Okay, I'll draw the three-dimensional view of this stress element. Then I am going to consider the unit thickness to this normal to this paper. I am going to put the unit thickness of stress element. Okay, unit thickness, this thickness is 1. This that is in normal to the plane. On this plane, what is the stress acting on this plane? Sigma r plus d sigma r. On this plane, the sigma r stress is acting. On this plane, what is the stress acting? The sigma t. On this plane, the sigma t stress is acting. Okay, and these are the stresses acting on this stress element on a finite dimension stress element. Then this dimension, what is the unit length. Then what is the thickness? Thickness is equal dr. Okay. I think you will more clear how to mark these stresses. Okay. Then I'm going to consider the force equilibrium of this separated stress element. The force equilibrium of this separated stress element. Then first of all, force equilibrium in a radial direction. Okay. Considering so I'm going to obtain the equation. Considering the force equilibrium in radial direction. Okay, radial direction. In this direction, that means in this direction, I am going to consider the force equilibrium of this separated stress element. So first of all, let me find this arc length. What is this arc length? D theta, angle is d theta into r plus dr. What is this arc length? d theta into r. Okay. Okay. Let's find the force equilibrium for this stress element. Let me write the equation. Okay. In this direction, what is the force acting? Stress acting is equal to sigma r. Then what is the cross sectional area this sigma r is acting? Sigma r is acting d theta r into 1. Okay. That means the sigma r into d theta into r into 1. Okay. This means the area at this sigma r is acting. That means area into sigma r we are getting the force. Okay. Then at the same time this force, that means this residual component of this force also we have to consider. It means the sigma t from the, because of this sigma t, what is the force acting? Because of this sigma t, what is the force acting? Because of this sigma t, this area is equal dr into 1. Okay. Plus there's a two faces as then what is the force? Sigma t into dr into 1. Then we have to consider the residual component in a radial direction, sine d theta divided by 2. Okay, sine d theta divided by 2. That is equal to force generated by this stress element. What is the stress? Sigma r plus d sigma r into what is the area? Area of this face. Okay, area of this face, that is equal to 1 into uh, d theta into r plus dr. Okay, this is the equation we obtain considering the equilibrium of this stress element in a radial direction. Okay, here we have marked all the stresses acting on this stress element. Then we consider the equilibrium of this stress element in a radial direction. So let me simplify this obtained equation. Okay, you all know for small angles, so, the sine theta value is equal to its angle in radian value. Okay, that means the sine d theta divided by 2, we can write it as d theta divided by 2 approximately. This is in radian. So the instead of this term, I'm going to put the d theta divided by 2. Okay, d theta divided by 2. Okay, you all know that one. Okay, let me write that one. Sigma r into d theta into r plus 2 sigma t dr d theta divided by 2 is equal to sigma r plus d sigma r d theta r plus dr. Okay, r plus dr. Then we can cut this one. Then again you can see the d theta is common term, so I'm going to cut the d theta from the entire equation. D theta, here also d theta, here also d theta. Then our equation reduced to r sigma r plus here sigma t dr is equal to r plus dr into sigma r plus d sigma r. Okay, d sigma r. Okay, then further we can simplify this equation. R sigma r plus sigma t dr is equal r sigma r plus r d sigma r plus dr into sigma r into, you can see the here dr into d sigma r. Then you can, here you can see the multiplication of two small terms. That is we can equate to 0. We can equate this multiplication of these two terms. Okay, that will equal to 0. So then we can equate this one. Here also you can see this r sigma r. We can cut that one also. Okay. Then finally we are remaining sigma into dr is equal, we are remaining this one, no? R d sigma r plus dr sigma r. Okay. Then the entire equation I am going to divide by the dr. Then finally we are having this kind of equation. Okay. Then sigma t is equal r d sigma r dr plus sigma r. Then by taking this in the one side, sigma t minus sigma r minus r d sigma r dr is equal to 0. Okay. I think you all got no clear idea how to obtain this equation. Just let's mark this equation as equation A. Let's mark this equation as equation A. This equation is A. Okay. Page 2. Okay, then I am going to consider the infinitely small, if we take the infinitely small stress element. Okay. Then I am going to consider the infinitely small stress element. If we consider the infinitely small stress element from this r distance from the radius, okay, on that stress element we can mark the stresses. On that stress element we can mark the stresses like this. In a radial direction, sigma r. In a tangential direction, sigma t. Here also sigma t. That means we can consider the stress developed in this cross section as the biaxial stress system. Okay, biaxial stress system. Okay. Then let's take the elastic modulus of the material as the E. Okay. Then the Poisson ratio as the nu. I think you all know these two terms, what is meant by the elastic modulus of the material and the Poisson ratio of the material. This is a material property. So let me, if you are not familiar with this Poisson ratio, what is meant by the Poisson ratio? The Poisson ratio is a material property that is defining in this way the absolute value of the, if the stress is if the stress element is subjected to biaxial stresses or triaxial stresses, we are relating the transverse strain to a axial strain using the Poisson ratio. Here the Poisson ratio defining in this way in a biaxial stress system, strain in a transverse direction to strain in axial direction called the Poisson ratio. What it means, if we are stretch the element in this direction, okay, if we stretch, that means because of this sigma r, that will stretch in r direction. While stretching in r direction, it will contract in this direction, in a transverse direction. That means in a transverse direction it contract while stretching in radial, according to this figure, radial direction. Okay, that means the ratio in a transverse direction to axial strain called the Poisson ratio. It's a material property. It's a material to material that is vary. We take the elastic plastic like material, that is very high. The Poisson ratio is very high. Okay, in this level you should know this ratio. The actually this ratio, you can see these strains are in two different directions. The one is contracting, one is extracting. So this inner ratio is negative. So to remove this, always this ratio is negative for biaxial stress system. So then to remove this absolute value, what we are doing, we are multiplying with the minus sign. Okay, axial transverse direction, the axial direction. Okay, then we are having the equation. Yeah, minus strain in transverse direction is equal to nu into strain in axial direction. Okay, axial direction. Okay, using this I just refresh your memories about the Poisson ratio here. Then let me write the equation for strain in for this application, for our thick wall cylinder application. I'm going to write the strain in radial direction and the tangential directions. Okay, let me write the equation for strain in radial direction. Okay, because of the sigma r, what is the amount of stretch? You know this equation, the sigma is equal E into epsilon. Epsilon is equal sigma divided by E. In a radial direction, what is the strain? Because of the sigma r, it is equal to sigma r divided by E. Sigma r divided by E. Okay, sigma r divided by E. Then because of the Poisson effect, when stretching in a tangential direction, there are also contraction in radial direction. Okay, because of the Poisson effect. So we have to subtract this one. That transverse strain we can calculate in this kind of manner. Transverse strain nu into sigma t divided by E. Sigma t divided by E. Okay, sigma t divided by E. Transverse strain. Okay, transverse strain is equal to minus into nu into axial strain. Okay, at the same way we can write the strain in tangential direction, that is equal to sigma t divided by E minus nu sigma r divided by E. Sigma r divided by E. Okay, we are having the two equations for strain in radial direction and the strain in tangential direction. Okay, I will multiply this one with E. E into epsilon r is equal sigma r minus nu into sigma t. E into t is equal minus nu into sigma r plus sigma t. Okay, sigma t. Let's take this equation as equation. So what is the equation previously obtained? Yeah. Let's take this equation as equation 1. Let's take this equation as equation 2. Okay, equation 2. Okay. Then I am going to multiply the equation. Yeah, I'm going to simplify this both the equation to obtain the value for sigma t, expression for the sigma t. So then when we are going to obtain equation for the sigma t, I'm going to multiply this one with the new. I'm going to first one I'm going to multiply with the new, and we are having e into epsilon r into new is equal sigma r into new minus new square sigma t. Let's take this equation as equation 3. So I am going to add these 2 and 3. 2 plus 3 I am going to add. So then we are obtaining E strain in transverse direction plus strain in radial direction into nu. This one we can cut these two. So then we are remaining here sigma t 1 minus nu square into sigma t. Then we can further simplify by making the sigma t into subject. By making the sigma t into subject. By making the sigma t into subject, we are getting E divided by 1 minus nu square strain in tangential plus Poisson ratio into strain in radial direction. Okay, then let's take this equation as equation 4. We need this equation later. By following the same procedure, we can obtain for the sigma r. That means by multiplying this equation with the equation 2 with the new, then by adding we can obtain the equation for the, that means by multiplying the second equation with the new, then by adding these two equations, obtain equation and the equation 1, we can obtain the equation for the sigma r by following the same procedure. This is the equation we are obtaining for the sigma r. So I will directly write that equation epsilon r plus nu into epsilon t. Just take this equation as equation 5. And these two equations we need later. Okay. Okay, then I am going to obtain the strains, the expression for the strains consider the deformation of this thick wall cylinder. Okay, again I am going to obtain the two expression for epsilon r and epsilon t considered in the deformation of the cylinder. Okay, let's see how to obtain that one. Okay, this is our, let's take this is our thick wall cylinder. This is our thick wall cylinder. Okay, then let's take the stress element. Let's take the stress element. Okay, then this is the initial position of this stress element. Let's take the initial position of the stress element. Okay, then because of the, let's take for example in this situation, let's take it is subjected to a stretch in outward direction. That means it is subjected to a internal pressure, so that it will let's assume that it will expand in outward, so that that means this stress element is displaced in a radially outward, like this. Okay, like this. So I will enlarge this two stress element in this kind of manner. Okay, this is the radial direction. Then this is our first stress element, considering before applying the pressure. Okay, before applying the pressure, then after applying the pressure, it has let's take it has displaced to a this kind of position. Okay, just take that means this wall has displaced to this kind of position, then this wall has displaced to this kind of position because of the internal pressure. Okay, internal pressure. Let's take this displacement. Let's take the displacement function as the u. It's a function of r. Okay, displacement function. Then how this cylinder's radial points are displaced with respect due to the internal pressure. Oh, see, when a cylinder under pressure, called represented by the displacement function ur. Okay, then in here, what is the strain in radial direction considering the this displacement? This position, that means if you take the r distance, that means this is the r distance. Okay, if you take the radial from the radial position to this position, the distance is equal to r. For this position to from the radial position, that is equal to r plus dr distance. R plus dr distance. This distance is equal to r. Then if you know the, let's take this is the displacement function. What is the displacement of this a point? Let's take this is a point has displaced to a dash point. Then this the b point has displaced to a b dash point. What is the displacement of a dash point? This one is equal to, this one is equal to ur. Okay, that means this displacement, that means a dash length is equal to ur. Okay, then what is the b dash length? b dash length is equal to displacement of this point u r plus dr. ur plus dr. Okay, ur plus dr. If you take this stress element, what is the stretch, amount of stretch? Okay, then that will stretch, the amount of stretch, that means this is the extent, this is the what is the stretch? The amount of stretch for this this length, that is equal to u r plus dr minus ur, the amount of stretch of this stress element. Okay, then how to calculate the strain? Strain in radial direction, that is equal to divided by original length. What is the original length of this stress element? AB, that is equal to dr. That is equal to dr. Then what is this? For the from the basics of derivation, that is equal to epsilon r is equal to du over dr. Du over dr. Okay, it's a derivation of the displacement function, that is equal to strain in r direction. Let's take this equation as let's take this equation as x. Okay. Then I am going to consider the strain in circumferential direction. Okay, strain in circumferential direction. Okay, then what is the new circumferential length? New circumferential length. Let's take this one. Let's take this AB. Let's take the C and the D. Now C dash D dash. Okay, C dash D dash. Let's take this one as d theta. Okay, d theta. Then what is C dash D dash? C dash D dash, that is equal to d theta into what is the radial distance? r plus ur, r plus ur minus d theta into what is the CD length r divided by the original length. What is the original length? D theta divided by r. Okay. In that way, we can calculate at an radial direction the tangential strain. We can calculate strain in tangential direction, that is equal to the, we can cut actually yeah, then d theta we can cut and r we can cut. That means the u divided by r, u divided by r. Let's take this equation as equation y. Okay, equation y, equation y, page 3, page 4, equation. So then we have written the strain developed in tangential strain and the radial strain using the displacement of the radial displacement of the radial displacement function. Okay, then I am going to substitute this x and y in the equation 4 and 5. Okay, here these the previously obtained the two equations, the equation 4 and 5. Instead of these terms, I'm going to substitute these are. Okay, sigma t and well, let me write that both the equation by substituting these values. Okay. Then I'm going to write the for equation 4. Let's take the equation 4. Sigma t, that is equal to E divided by 1 minus nu square for u divided by r plus nu epsilon r du over dr. Let's take this equation as equation 4, 5, 6. Okay. Then sigma r also we can write E divided by 1 minus r square, the epsilon r du over dr minus plus nu u divided by r. Let's take this equation as equation 7. Okay. Then here you can see we have found the sigma t and sigma r as a function of displacement, and these both the equation 6 and 7, I'm going to substitute in equation A. What is the equation A? This one. Okay, sigma t I'm going to substitute in here, sigma r I'm going to substitute in here. Okay, let's obtain the equation by substituting these two sigma t and sigma r values in the equation A. Okay, so let me substitute these values. You all got a clear idea up to now. I think you all very clear with this calculation. Okay, everything clear, no? Okay, then I'm going to substitute this sigma r and sigma t in this equation. Okay, sigma t, what is sigma t? E divided by 1 minus r square u divided by r plus nu du over dr. Then minus sigma r minus E divided by 1 minus sorry, here 1, yeah, sorry, new is square, no, this new is square, sorry, new is square, okay, yeah, yeah, new is square, okay, then here it is a new square, then du over dr plus new u divided by r, then minus r d sigma r, the derivation of sigma r, e 1 minus new square du over dr plus new u divided by r, dr is equal to 0, dr is equal to 0, okay. Then here you can see in this equation, okay, in this equation this term is common, so we can cut this term is a non-zero value, there we can cut this term, okay. This one is a common because we can take it out from the derivation, it's a constant, so we can cut that value, okay. Then let's take, I will write that equation. Here u divided by r plus new du over dr, here minus du over dr minus new u divided by r, then the minus r into the derivation of this one. So what is it? How to take the derivation of this one? Okay, first of all I will write that one. Let me write that one. Du over dr plus new u divided by r, derivation of dr is equal to 0, okay, equal to 0, okay. Then the derivation of this one, here it is multiplication, no? Multiplication, okay. So then what is the derivation of this one? I will write that term r, this derivation d2 u dr square plus new, then division of two functions, that means u and r, so that we have to take we have to consider the division of two functions, that means r into du over dr then derivation of this one is equal to 1, no? Yeah, the square is equal to, sorry, that is equal to 0, then I will add these terms u divided by r plus new du over dr minus du over dr minus new u divided by r, okay. This one is equal to 0, this one is equal to 0. Then let's remove this brackets, u divided by r plus new du over dr minus du over dr minus new u into r minus r d2u dr square minus here is a r, one r we can cut, that mean here I'll write that one, minus r nu du over dr divided by r square, so that 1 over r minus so being the plus nu u divided by r, that is equal to 0. Okay, so then we can further simplify this one. We can cut this one, no? We can cut this one. Then the u divided by r. Then again, here this one should this one there's a 2 r square, no? R square, then this one is okay. This one not there. So then we can cut this one also, no? We can cut this one also. Then finally we are remaining this one. Minus du over dr minus r into d2u dr square is equal to 0. So then entire equation I am going to divide it by r, u divided by r square minus 1 over r du over dr minus d2u dr square is equal to 0. Okay, then I will write by multiplying minus 1. By multiplying the minus 1, d2u dr square plus 1 over r du over dr minus u divided by r is equal to 0. Okay, then you can see the second order differential equation we are having. Second order differential equation we are having. The second order ordinary differential equation. Then the solution of this differential equation. The solution of this differential equation in this kind of format. The ur is equal to c1 r plus c2 divided by r. That means this is the solution of this differential equation. That means we can satisfy this differential equation using this solution. Okay, using this solution. Then this c1 and c2 are constants. Have to determine considering the boundary conditions. Okay. In this differential equation, this is the actually we are obtaining the differential equation of the displacement function. Displacement function in this kind of format. That means this is the solution of this differential equation. We can satisfy this from this solution. Then the c1 and c2 are constants. Have to determine considering the boundary conditions. So then then we are going to find the c1 and c2 constant considering the boundary conditions. Let's see how to find these two constants, c1 and c2, considering the boundary conditions. Okay. First of all, we are having the equation for sigma t and sigma r. Then I'm going to substitute here sigma t equation and sigma r equation. Then this u function I'm going to substitute in this equation. Then we are going to substitute boundary condition to find the unknown C1 and C2. Okay, that means this solution I'm going to substitute in equation 6 and equation 7. Okay, in here I'm going to substitute this equation. Okay, let's see how to substitute that equations 6 and 7. Okay, okay, let me take this equation. The UR, we have obtained this UR function as in this kind of format. Okay, C2 divided by R. Okay, then this one I'm going to substitute in this equation 6 and 7. Let me substitute that one. Okay, the sigma t function. Okay, sigma t function. Sigma t is equal the E divided by 1 minus mu square, then the U divided by R, C1 plus C2 divided by R square plus nu du over dr, derivation of this function with respect to R is equal to C1 minus C2 divided by R square. Okay, into nu, no, here it is nu. Okay, sorry, here it is nu, no. Yeah, sorry, this is a multiplication. Okay, multiplication. Then the sigma R we can write E divided by 1 minus mu square du over dr, C1 plus minus C2 divided by R square plus nu into U divided by R, C1 plus C2 divided by R square. Okay, then sigma t we can further rearrange. Rearrange sigma t is equal E divided by 1 minus mu square. I'm going to take the C1 part separately, 1 plus mu plus C2 1 minus mu divided by R square. Then again sigma R we can rearrange. Sigma R is equal E divided by 1 minus mu square C1 1 plus nu minus C2 1 minus nu into R square. Just take this equation as a the equation we mark equation 6, 7. Just take this equation as equation simple A, equation simple B. Okay, I think up to now you all more clear how to obtain these equations. Okay, very clear. Okay, everything clear. Okay, we are having the sigma t and the sigma r equations. So then in this equation, our objective is to find the equation for sigma t and sigma r. Here the problem is the sigma C1 and C2 are unknown constant. These C1 and if you can determine C1 and C2 constants, we are having the equation for sigma T and sigma R. Let's see how to find this C1 and C2 constant using the boundary conditions. Then what are the boundary conditions? Okay, let's take the situation cylinder under internal and external pressure. Okay, let's take the thick wall cylinder. Okay, the external pressure P out, the internal pressure Pi. Okay, Pi and the P out. Let's take, I mark this pressure in this way, kind of manner. Okay, then external pressure acting in this direction. Okay, then what is the radial? Let's take this one also. The internal radius as A, external radius as B. Okay, external radius as B. So then what is the stress, radial stress? Sigma R, R is equal A. Okay, one boundary condition. That means stress at R is equal A. What is R is equal A mean? Inner surface. Inner surface stress. What is the inner surface stress? What is the inner surface stress? If we take the inner surface, this is the inner surface. What is the stress acting on this inner surface? If we take the stress element on this face, what is the stress acting? What is the stress acting? The stress mean the pressure, no? Pressure. That means the force per unit area, that means the pressure. Okay, this is the open to the inner, so that the pressure on this surface is equal to pressure, internal pressure, Pi. Okay, Pi. That means there is acting inward to the stress element, considering stress element. But we have to consider the sign. Positive stresses we are marking outward from the stress element, so that this one is equal to minus Pi, minus Pi. Okay, minus Pi. Okay, then if we take the sigma R, R is equal B. What is the value? R is equal B. R is equal B. What is mean R is equal B? R is equal B mean outer surface. If we take the outer surface like this, what is the pressure? P out. That is acting on this surface inward to the this kind of pressure is acting. P O pressure is acting on the surface. If we take the stress element like this, okay, that is acting inward. Mean this P not mean the pressure, that means is called stress acting inward to the stress element, so that is also a minus P. Okay, and two boundaries we know the Pi and two pressures are two stresses are we know. Okay, at the two boundaries, what are the two boundaries? R is equal A, R is equal B. We know the stresses, sigma R values. Then we can develop the two equations. Here we are having the two unknowns. Then we can find the C1 and C2 unknown constants. That is the way we are going to find the C1 and C2 unknown constant. Let's see how to find that one. Okay. First of all, I am going to write the equation considering this first boundary conditions. Okay. The minus the Pi considering the first boundary conditions. E divided by 1 minus nu square, the C1 1 plus nu minus C2 1 minus nu. Here what is R square? Instead of R square we have put the A square. Okay, now A square. Consider the second boundary condition. I am going to write the equation minus P naught O E minus 1 minus nu square C1 1 plus R minus C2 1 minus nu into b square. Okay, then let's take this equation as equation C, this equation as equation D. Okay, equation D. I'm going to subtract. I'm going to subtract. I'm going to subtract C, CD. Okay, I'm going to subtract these two equations. Okay, in here I'm going to consider the C minus D. Okay, equation C minus equation D. Okay, here we are having P naught minus the Pi. I'm going to multiply same at the same time. I'm going to multiply the 1 minus nu square, 1 minus nu square divided by E is equal. We can cancel out these two, so we are remaining C2 1 minus nu divided by b square minus C2 1 minus nu divided by a square. Okay, so then in here we can further simplify this one. P naught minus the Pi 1 minus nu 1 plus nu divided by E is equal C2 1 minus nu the b square C2 1 minus nu a square. So then we can cut this one. So finally we are remaining P naught minus the Pi 1 plus nu divided by E is equal, by taking the C2 out, okay, a square minus b square divided by a square b square. Okay, by making the C2 into subject, the C2 into subject, P naught Pi 1 plus nu a square b square divided by E a square minus b square. This is C2. Okay, this is C2. This is how we are finding the C2. Okay, this is how we are finding the C2. Okay, then I am going to find the C1. Okay, to find the C1, this to find the C1, I am going to remove this term. Okay, I am going to remove this term. So we have to divide it by this equation. We have to divide it by b square. Then this equation we have to divide by a square. Then we can by subtracting these two equations, we can remove the C2 terms. So then we are having the C1 terms equations. Okay, so first of all I am going to divide this C1 equation by a b square. Okay, then you are going to find the C1. Okay, sorry. Okay, by dividing the C equation by b square, we are having Pi minus Pi divided by b square. That means C, sorry, let's take this equation, E divided by b square, same equation, Pi b square 1 minus nu square divided by E, C1 1 plus nu divided by b square minus C2 1 minus nu divided by a square b square. Okay, then equation F also I am going to divide it by a square. Okay, minus p naught divided by 1 minus nu square a square divided by E is equal c1 1 plus nu divided by a square minus c2 1 minus nu b square a square. Let's take this equation as ef. Let's take g and this equation as h. Okay, to remove the c2 terms, I am going to subtract g minus h. Okay, from g minus h we are getting p naught 1 minus nu square divided by e minus pi 1 minus nu square divided by e is equal c1 b square minus 1 over a square. Sorry, in this equation p naught divided a square, here b square. Then we can further simplify to find the c1. I'm going to take p naught divided by a square minus the pi divided by the b square. We can take out 1 plus nu 1 minus nu divided by e is equal c1 here a square minus b square a square b square 1 plus nu. Then we can cut this. Okay, here also 1 minus nu divided by e b square p naught minus a square pi divided by a square b square is equal c1 a square minus b square a square b square. Okay, by making the c1 into subject, 1 minus nu divided by e a square a square pi. I'm going to change the terms by multiplying the numerator and denominator by the minus sign. A square pi minus b square po divided by b square minus a square. Then this is the c1. This is the c1. Then these c1 and c2 constants. Okay, this is c1 and c2 constants. We are going to substitute in equation so yeah, we are going to substitute in equation a and b to find the expression for sigma t and sigma r. Then we can obtain the equation for sigma t and sigma r. Okay, let's see how to substitute c1 and c2 and to obtain the equation for sigma t and sigma r. Okay, let's take the equation a. First of all, I am going to substitute c1 and c2 in the equation a. Okay, from equation a for sigma t is equal e 1 minus nu square. What is c1? 1 minus nu divided by e a square pi minus b square po divided by b square minus a square. Okay, c1 plus c2 into c2. What is the value for c2? We will obtain c2. This one c2 po minus pi 1 plus nu a square b square divided by E into a square minus b square into 1 minus nu divided by r square. Okay, this is sigma t. This is sigma t. We can further simplify this equation. Okay, sigma t equation is equal, we can cut this one. Okay, here only remaining 1 plus nu. Yeah, you can cut this one also. Then we are remaining the 1 plus nu. Yeah, sorry, here it is c1 1 plus c1 here there's a 1 plus nu, no, there's a 1 plus nu. Here also c1 into c2. Here in the c2 there's a 1 plus nu, no. Yeah, 1 plus nu. Okay, then this one we can cut, no, these terms we can cut. So we are remaining this one a square pi minus b square po divided by b square minus a square plus. Okay, I'm going to multiply the both numerator and denominator with the minus sign. So then we are getting pi minus the po a square b square divided by r square b square minus a square. Okay, this is the equation we are obtaining for sigma t. Okay, this is the equation for sigma t. Okay, so then let me obtain the equation for sigma r also. So what we are going to do, we are going to substitute c1 and c2 in the equation b. In this equation I am going to substitute c1 and c2. Okay, see how to substitute that one. Sigma r equation, e divided by 1 pi minus nu square 1 plus nu. What is c1? c1 1 minus nu divided by e a square pi minus b square po divided by b square minus a square. Then minus c2, I will write that this one 1 minus nu divided by r square into c2. What is c2? c2, this is c2 po minus pi 1 plus nu a square b square divided by e into a square minus b square. Okay, then we can cut these e with this one. So finally we are remaining for sigma r, we are remaining this one a square pi minus b square po divided by b square minus a square minus, I'm going to multiply both sides by minus sign, pi EO A square B square divided by B square minus A square into R square. Then this is the sigma R equation, radial stress equation. Okay, in that way we can define, we can obtain the equation for sigma R and the sigma T in this kind of manner. Okay, this is the sigma T equation, this is the sigma R equation. Okay, that means if we take the thick wall cylinder under internal pressure and external pressure, okay, with the radius of internal radius of A, outer radius of B, if we take a certain point R distance from the center, stress developed on this point we can represent by this kind of diagram, this kind of infinitely small stress element, sigma T and sigma R. Okay, then this sigma R we can determine using this equation. Okay, then the sigma T we can determine using this equation by putting the relevant R value in this equation. R is the variable. You can see the sigma R is a function of R, sigma T function of R. By putting the relevant R value, we can find any point stresses on this thick wall we can calculate. Okay, if you know the sigma R and sigma T, then we can go for the further analysis of this thick wall cylinders. Okay, these are the basic equation to determine sigma R and sigma T. Okay, I think you all got a more clear idea about this one. Okay, then next day class we are going to discuss, we are going to reduce this equation considering the situation, the cylinder under internal pressure only situation, and also cylinder under external pressure only situation. We are going to reduce these equations, and next day class we are going to discuss also string fitting. Okay, string fitting, the stress developing string fitting cylinders. Okay, let's continue next day class. Thank you.